Sorry?
We need you to log into the computer here.
Are you using the computer?
Yeah, I am. Just as soon as you answer this question, I'll move to the computer. So I will log in.
Can you log in first? Or do you need to...
Sorry.
So because like when we connect to the computer, like we can't do it when you're midway.
Yeah, okay, okay.
Set it up now.
Or, oh, sorry, you are the guys with the. I thought you were students. I thought you were students. Okay, no, I will. Yeah, sorry about that. Okay, so do your thing. Okay. Good, thanks, yes. Yeah.
Is the air conditioning on?
I just started. It's running now. Yeah. Yeah, thank you. Thanks. Thanks. Okay, guys. There are plenty of chairs on this side. So transfer function, what is it? You have a system, the system has its transfer function. What does that mean? This course is packed with transfer functions. So you will really need to know what it is. Have an idea what it is if you don't know the exact definition. So what is it? Output or input? Are we all happy with that answer? So if x of t is the input function, y of t is the output function, or input signal, output signal. The transfer function, according to the answer I think I heard, was y of t over x of t. Is that correct? No. Someone said. Why is it not correct? Okay. Because this is y is a function of t, x is a function of t. So we are still in the time domain. In the time domain, this relationship has no meaning at all. This means nothing. But if you find the Laplace transform of x of t, so you get x of s. If you find the Laplace transform of y of t, so you get y of s, then y over s over x over s. We use capital G for that. This is the transfer function. So this is the transfer function. So you have to move into the S domain. And then this transfer function here describes the system. It is, once again, it is the system. You can think when you have G of S, you know the system. In the time domain, to describe the system, you use the differential equation that describes the relationship between the input and the output in the time domain. So what is differential equation in the time domain? That's what transfer function is in the S domain, complex domain. Okay. Now, knowing this relationship or definition of the transfer function allows you to do a number of things. Once you know the transfer function, that is the system. So you can apply different inputs, and you will know, so even before you apply the input, you know what the output is going to be. Because you know the transfer function, you decide to apply an impulse as the input, you multiply the input with the output, with the transfer function in the S domain, and you will get the output. You change the input, you will get obviously different output. In the time domain, especially those that are more complex, where the differential equations are of a high order, you will most likely have to apply a certain input and then try to find out what the output is each time you change the input. Now, to answer one of the questions on the discussion forum, because I know at this stage students are still not sure about initial conditions, for example. How initial conditions affect the transfer function? Well, the answer is they don't. The transfer function does not depend on initial conditions. The transfer function depends only on the relationship between the input and the output. Any input and any output. The transfer function also does not depend on the form of the input. So no matter which function you apply as the input, what is the form of the input, transfer function is the same. The output will change. An example I used earlier, a spring mass damper system. Input force, output displacement. So we said earlier, if we regard this M as a free body, so analyze the free body diagram, you will have force as the input minus force in the spring. Those are the only two forces acting on M, will be equal to inertia, to mx double dot. So mx double dot equals F minus, but the force in the spring will be equal to Kx. Rewriting this will give us F equal to mx double dot plus Kx. Apply the Laplace transform on both the left-hand side and the right-hand side of this differential equation, assuming that initial conditions are 0. Because when you're looking for the transfer function, you assume initial conditions to be 0 in order to get the transfer function. Laplace transform of f of t will now be only f of s. Laplace transform of mx double dot, m is a constant, but because of the double derivative, you will have s squared times x of s. The other two terms, if you check the equation from the lecture notes, the other two terms will be 0 because we assume initial conditions to be 0. Plus, k is a constant. Laplace transform of x of t will be capital X of s. Transfer function, g of s, will be equal to output x of s over input f of s, which will be equal to 1 over ms squared plus k. So, in the time domain, this is how we describe this particular system, spring mass system. In the S domain, this is how the same system is described. Knowing the transfer function enables us to apply any input we want. So f can be any function we want, as long as that function has its Laplace transform. So we can multiply f of s with this transfer function. That will give us x of s. Then that x of s output needs to be inversely transformed by Laplace to get x of t. And then you see what this system is really doing. What is the output of the system? An example, I'm not deriving that. We'll do a number of these examples later. But imagine this force is just an impulse. So you just flick that mass. What will happen? The mass will oscillate. So we kind of know that. Without deriving that sinusoidal expression, we know that the mass will oscillate. If you apply a different function, if you apply a step function, so apply a force that stays constant, then the mass will oscillate, but not about 0, but some other value. We'll see what that value is. So that changes the output. As you change the input, you change the output. You apply any other function you want, the output will be different. But the system is still the same system. So the system will not change because you apply a different input. How about initial conditions now? Well, they don't affect the transfer function. But if you apply your input, your impulse, your flick, when initial conditions are 0, that's very easy. So that's when you apply input with transfer function, you get the output. But if initial conditions are not 0, so if your mass is already oscillating for whatever reasons, for whatever was happening before time was 0, then the output will be different, because depending on when you apply, when on this sign, when the mass is oscillating, when you apply your impulse, the output will be different. Because initial conditions can be different anywhere along this sine function. So initial conditions will affect the output, but they won't change the system. It is the same system. Therefore, it is the same transfer function. So those who are already going ahead with, excuse me, with set 2, is it question 6 or question 7? So you're given a differential equation, and part A asks you to find the transfer function, part B asks you to find the output. Or is it the other way around? Well, we can check that. When we ask you to find the transfer function and we give you initial conditions, that is a trick question. Ignore initial conditions. Find the transfer function with all initial conditions equal to 0. All initial conditions are 0. That's where this transfer function applies. as I said, the output will be different. So the question B, if it is B, find the output, then you have to go back to your differential equation. When you do Laplace transform, you can't ignore the initial condition, those terms corresponding to initial conditions. And as a result, the output will be different than when initial conditions are 0. Okay, so that was one issue. I didn't really want to spend too much time typing on the forum. And now that some of you can unsubscribe, though they won't be able to see that anyway. So I think it's better to say it here and explain in detail. And of course, answer any questions that you may have now. If not, there was another issue from the discussion forum, and that's about this shift theorem. And now I'm going to use exactly the same example as in the lecture notes. So duty cycle. So when this function, so this is a ramp function, and when this function reaches the value of A, yes, and it reaches the value of A when time equals to B, then the function drops to 0 and stays 0 until infinity. Now, finding the Laplace transform of this function is not as simple as it may look like. Yes, it is true that this is A over BT. But when we write this, we assume that this function is growing until infinity, which is not the case. So we can't simply find inverse Laplace of this from the tables, which is easy, and say that is the answer. We have to include this thing happening here. So what we did, we said that this function was what we said in lecture notes, equals to, first of all, it is equal to this ramp function that carries on till infinity. And that one is A over BT. Plus, after B seconds, you have this ramp function, which is the slope of the transfer function is minus A over B times T. When you combine these two, what you get is something like this. So this is A, this is B. Okay, I'm talking only about the slope. I'll get back to the exact analytical expression of what we have here. But just I want you to understand this. Between 0 and A, you are adding these values and zeros, so you are getting the same values. From B onwards, you have this minus this. Here you have this minus this minus this. So you end up having a constant here. However, this is not the same as this. So you have to add a step function, magnitude minus A, also after B seconds. Sorry, you can't see this. So these three, when combined, will give you this original waveform or the original function. Now, can we find a Laplace transform of this function? Yes, we can. This is a ramp function. Check the tables. It will be 1 over s squared times the value of the slope, A over B. This one is not that simple. So maybe the lecture notes are too brief. In this particular case, we said, OK, it is a negative ramp function, the same slope, shifted by B seconds. And we kind of expected you to just take it face value. So if you don't take it face value, that's good. You demand the explanation, and you will get an explanation. full explanation. So don't just believe us. We might be wrong. Very often we are. Sometimes we are not. And so let's see how we express this function here. So we can apply a Laplace transform to this. This function, when expanded to the other side, this point here will be A. Okay? Because if this is B and the slope is A over B, or minus A over B, so when expanded, it crosses the vertical axis at A, capital A. So this function only, the way it is written, will be A minus A over B t. Okay. However, I don't want this function to exist before time reaches B. Otherwise, if it does, that will simply cancel with the function that is already there. I want between 0 and B, I want only this to exist. I want 0 here, I want 0 here. How do I achieve that? I'm going to multiply this by u of t minus b. By doing this, I'm actually restricting this function to 0 until time reaches b, and then it becomes this negative ramp function. So this indicates a shift in the time domain. Okay? So we want to apply the shift theorem, time domain shift theorem, to this function so we can get the expression for this function in the S domain. But we can't because here we have a shift, but here we don't. So I'm going to rewrite this as A minus A over B, T minus B plus B, U of T minus B. This is the same as this, you all agree. But then, I want to keep this. I need it. So only if I have t shifted by the same amount everywhere in this function can I apply the shift theorem. So I'm keeping this, but this b I will multiply by a over b. So this becomes a minus, now I'll keep this, a over b, t minus b, and minus b times a over b will give me a, u of t minus b. So I'm really happily and positively surprised to see a and minus a canceling each other. So I end up with minus a over b, t minus b times u of t minus b. Now I have t shifted by the same amount everywhere in this function. So now I can apply the Laplace transform. I can apply the shift theorem to get the Laplace transform of this function. Okay. So if the Laplace transform of this function here was a over b times 1 over s squared, because we have a ramp, here Laplace transform will be minus a over b times 1 over s squared, because it is a ramp function, but the ramp function shifted by b, and therefore I have e to the minus bs here. which is what you have in your lecture notes. And let's focus on the third one. It is a step function, but it is a negative step function. So it is negative step function magnitude A times, oh, you can't say it. So it is a negative step function magnitude A times 1 over S, because Laplace transform of a step is 1 over S. And then we need to apply this shift, e to the minus bs. So combining now these three components, we get this function in the S-domain. But the second one is probably the most confusing one, so I did it step by step to show you that eventually you're going to have a ramp or a negative slope, but shifted by b seconds.
What if you multiply the very first graph by the step function?
This one.
The very first one.
Or, oh, this one, nothing will change. Because multiplying by a step function means you multiply the function here by 0, nothing changes. Then here you multiply it by 1, so nothing changes. So this is, it's nothing wrong saying this is equal to.
Yeah, but if you multiply by a difference of step functions.
Oh, shifted function. You mean?
Like multiply by u of t minus u of t minus b.
This one?
Yeah.
Okay, then this function will not exist. So in that case, okay, so you have, just in case you, okay, so if you have, what did you say? So a over b t times u of t minus b.
No, times u of t minus u of t minus b.
Okay, you will, no, that's okay, just dictate this to me. So a over b times,
T
okay,
times brackets u of t.
u of t,
Yeah, minus u of t minus b.
okay. This would not be a description of this function because, let's expand it. So a, b, t, u of t. That's okay. That is this function, this ramp that goes forever. Minus a over b, t, u of t minus b. This part will look like this. First of all, it will start here. The slope will be minus a over b. But until b seconds, it won't exist. So this function, the second term would look like this, jump down here, and then continue. Which is actually correct. So combining these two, okay, combining these two will give us this. Absolutely. Okay, that's okay. No problem.
I found it easy to do it that way, but you have to expand it and change the t minus b into that.
Yeah, but you still have a problem getting inverse. You still have to artificially create the shift here to get this. So I don't mind. So this is correct. This is correct. I somehow, I think that the logic is easier to explain here, breaking the existing function into simpler functions, impulses, steps, ramps, or anything else if necessary. This is kind of not visible. Maybe it is visible to you, maybe it is visible to some of you. To me, I find it hard to explain why. As correct as it is, I find it hard to explain why this is correct.
Well, you can put in values smaller than b into that second term, and
Okay.
then one line up.
Okay. Oh, okay.
Yeah, so you put values less than b, and you can see when that whole term will be 1, the whole thing in the
Yeah. Okay, for time less than b, this is going to be 0 anyway. So you end up with this. So that's okay. So you have this. When time exceeds b, then you start having this. Okay? So you jump down. So this is the jump, minus a. So you jump down by A, and now this ramp offsets this ramp here, so it stays at 0. It's absolutely correct. No, this is correct. Having said that, analytically, you still need to create a shift, T minus B here, before you can apply the shift theorem. But it is OK. It is correct. Thank you. OK. Are we OK with this particular example? Oh, time is really flying. If not, the third point of contention, of dispute, was answers to tutorial problems. So I got, on Friday during the question and answer session, I got, I think, 5 or 6 people asking that. Then on the forum, at least 2 more asked that. Then I got emails, about 2 or 3 emails, students asking, are we going to get answers? Now, before I say yes or no, I'm going to try to explain something to you. I hope most of you will accept what I'm saying before I say yes or no. You are students. You attend lectures. Lectures are very theoretical. You don't know what to do with the knowledge you get. Then you need examples. You work on those examples in order to reinforce the theoretical knowledge you learn here. And you move on to year 2. You move on to year 3. You graduate. You go to industry. Everything sounds fine, apart from over 4 years, you're used to solving problems that you know have answers. And you know someone has that answer. And you create habits. That's the problem. We create habits throughout our lives. And some of those habits are not very good. So the habit of, someone tells you design a new car, probably not in the first year of your, of your career, design a new wheel for your car. Okay? You don't ask your supervisor, what is the answer? Because that's not, you are not paid to do something your supervisor already knows the answer to. You will be expected to create new answers, new solutions. And once you design your first wheel or your first, windscreen wiper or first car, then you step back and have an opinion about what you have just achieved. You have to learn how to evaluate your work. Does this make sense? Is this wheel, if it is rectangular, it's probably not a good wheel. You don't have to ask your supervisor, is it going to be circular? So you need to learn at some point, the sooner the better, to judge, to have an opinion about the answer you get. That's why we're actually not helping you, giving you answers all the time. Because as you solve those problems, you are looking to the answer. So you want your solution to match the answer. And you may get the answer without knowing exactly why that answer is the right answer. You're happy to get there somehow. I hope you agree with this. So it's not a good engineering practice. Thinking always, oh, there must be an answer, I just have to dig the answer somehow. You have to get to the answer yourself. Back to the real life here. You are students. You work sometimes away from university. You work on those examples. And of course, you are not experienced enough to know once you get the answer in linear systems from set 2, that is the right, that your procedure, you don't know that your procedure is right. It's not about the answer. You are not confident enough. That's all fine. That's all fine. And if you are in this building, you can just knock my door and ask me, well, am I doing something wrong here? And I can tell you yes or no. But if you're away from home, or if I'm not in the office, or if I'm pretending to be too busy so I can't talk to you, then you don't know where you are. You don't know how well you learned the subject. So that's why those answers are useful. Okay? And that's why I'm going to give you those answers. But before I give you that, I just felt I had to tell you this, that looking into the answer, trying to match your work to the given answer is not a good habit. It may help you for studying for the exam, but it's not a good habit. Just think about that. Now, what I'm going to do, as I said, I'm going to give you the answers. Where are we? So where are they? Tutorial set, tutorial answers. I just made them visible to you. Well, I didn't create Moodle. You know. They told me, oh, sorry, speaking of Moodle, the final problem, just quickly back to the camera, and that's those streaming videos. I don't know whether it is me or am I getting wrong instructions. Where is the camera? But actually, the way I was explained, once these guys do their job, they record the lecture, the lecture goes into a thing called Cloud Store. Okay. No, I'm not talking about transfer function here, input and output. Now, from Cloud Store, I need to download the file to my desktop. That's my transfer function here. Then my job is to upload this to the thing called the box. And right now, I left that uploading process is still going on. The last message I saw, it is transcoding. The video is transcoding, whatever that is supposed to mean. And then from the box, I have to link it to Moodle. That's my job. So obviously, you know, it took too much time, whether it is me or whether the instructions I'm getting are not right or whether the whole system is clumsy, I don't know. So I apologize. Once it is on the box, I have my little gallery, they gave me a gallery. So in the gallery, I will put those videos and I will link them to Moodle. I think, well, I wish this was possible, but I assume Moodle can't handle those big files. So once you use Moodle and you click to one of those lectures, you're actually watching them from the box, not from the Moodle. That's how I understand it. So I hope when I get back, the first lecture will be on the box. And then I will see, I hope I will be able to link it to Moodle. If it is me, I apologize once again. If it is someone else, then yeah, I'm not apologizing. I have enough trouble as it is. The good news, that's why I was, for a change, I was smart this year, not in the previous years. So I insisted that Echo was available despite this new system being introduced. So I had a little fight, but I kept Echo for this course. So by the time you get this, streaming videos or whatever we call them, please rely on Echo. I checked Echo on Internet Explorer. It works fine, or at least on my desktop. Some people are saying there are issues with other Internet browsers. Try Microsoft Internet Explorer. Until this is done, then, of course, enjoy seeing my face again on Moodle rather than in real life. OK, we spent probably a bit too much time. We still haven't finished lecture 2. Sorry, any questions, any technical issues or anything we said here? Let's at least finish lecture 2 before the break. So lecture 2. We're doing different partial fractions. We're doing different examples of how to use partial fractions to get inverse Laplace transform. So back from the S domain into the time domain. And we stopped here at example number 4. Question 4, calculate the response. Once again, I think we decided last time on Friday that response means output to a known input. Response is another name for the output of a system. But the response also assumes we know the input. So the input, in this case, is an exponential function. It says decaying because the exponential function has a negative argument. So it decays down to 0. So if this is the input and the transfer function is given here, the output is the product of the transfer function and the input. But the input has to be in the S domain. So Laplace transform of this exponential function is just 1 over S plus 1. Check the tables if you're not sure. Multiplying the transfer function with the input will give us the output. So output in the S domain looks like this. Two polynomials. The numerator is a second-order polynomial. The denominator is a third-order polynomial. The denominator is already factorized. So 3 real roots. What we need to do is now express VO of S as A over S plus 1 plus B over S plus 2, S plus 4 plus C over S plus 2. That is partial fractions. Then you join those three, A over S plus 1 plus B over S plus 4 plus C over S plus 2. Join them together. Equate the numerators. So this numerator will, with the newly created numerator, and find the values of A, B, and C. That's what we did last time. I'm not repeating the whole procedure. So you find A to be equal to 10, B is minus 1, C is minus 6. That means that subscript O is missing here. Output voltage equals to 10 over S plus 1, that's A, minus 1, so B is minus 1 over C plus 4, and C is minus 6 over S plus 2. Inverse Laplace of the first term, 10 over S plus 1, is 10 e to the minus 1 exponential function. Laplace transform of the second term is minus e to the minus 4t, because you have 4 here. And the third term is minus 6 e to the minus 2t, because of coefficient 2 here. Everything multiplied by u of t, I explained that last time. Okay, so this is not very different from what we did in the first three examples. Example 5 is different. Okay, so you're already given a function, say output of a system, and you need to find the same function in the time domain. You need to find the inverse Laplace transform of y of S. Why is this different? First of all, this root, S plus 2, appears twice because it is squared. We haven't had that so far. But we did say that one of the rules when using partial fraction method is that the root that is repeated has to be taken n times, where n in this case equals to 2. So first you take A over S plus 2, so that term is not squared. Second time you take B over S plus 2 squared. You have to do it. The other tricky part is this second polynomial, second term here, second order polynomial, S squared plus 2S plus 2. This one cannot be factorized. You can try, and you will find that this polynomial has complex conjugate roots. So it cannot be factorized. If it can't be factorized, then you still take it, but the numerator in this case has to be in this form, CS plus D, because you leave it as a second order polynomial. So the denominator here is a second order polynomial. The numerator has to be a first order polynomial. Okay. Now what you need to do is add these three fractions together to get one big fat function. And equate the numerators as you did so many times before. So this numerator is on the left-hand side, and this is your new numerator on the right-hand side, obtained from adding these three functions together, these three fractions together, or functions together. Now, this is a little bit tedious, because you can't do those little tricks. Maybe you can do to some extent, but you can't go too far. Little tricks we did before. So what you have to do really is go through the full procedure of equating coefficients of the polynomial on the left-hand side and polynomial on the right-hand side. So if you start with S cubed, on the left-hand side you don't have a cubic term, so you have 0. On the right-hand side, you have A multiplying S and then S squared, so that's S cubed. So you have A. B is not multiplying the cubic term, so here you have CS, and here you have S squared, so that will give you C. So 0 equals A plus C. Repeat the same for the second order term. So on the left-hand side, you have 2, so you have 2. Over here, you will have S multiplying 2S, so that gives us 2S squared, therefore you have 2. Okay, then you have 2A again, because you will have multiplying A multiplying 2 and multiplying S squared, and so on and so forth. If you find it easier, you can expand this expression, this expression, this expression, and then group all terms with S cubed, all terms with S squared, all terms with S to the power 1, all terms with S to the power of 0, and equate with whatever you have on the left-hand side. So this way, you get 4 equations with 4 unknowns, A, B, C, D. So you have a system of simultaneous equations. That is a little bit tedious, but the good news is that the results are not terribly complicated. So 2 of these terms are 0, and the other 2 are 1. Very nice. Now, that means if you go back, A is 0, B is 1, C is 0, and D is 1, back here. So, sorry, A is 0, so this term will not exist. This is 1, so we have 1 over S plus 2 squared. C is 0, good news, and this is 1 over S squared plus 2S plus 2. So here we are, 1 over S squared, S plus 2 squared rather, plus, sorry, it's here, 1 over S plus 2 squared plus 1 over S squared plus 2S plus 1. Inverse Laplace. This term, the highlighted term, is easy. It is case 6 from the tables. No, case 7. Did I say 6? Why did I say 6 when it says 7? Could be a little bit tight. So, case 7. T times e to the minus at will give us 1 over S plus a squared, and vice versa. So that is exactly what we have here, 1 over S plus 2 squared. Sorry, it's over here. So that will give us T times e to the minus 2t. That is an easy part. This term here, how do we find the inverse Laplace of this one? We said the first rule with inverse Laplace transforms is factorize the denominator. But we already know that it cannot be factorized. So when you go into your tables, you see that the functions on the right-hand side are all factorized. Okay? They're all factorized. Factorized, factorized. Okay, here they are not, here they are not. But when you get an expression like this, which is not factorized, this means that it cannot be factorized. So this expression here means that the roots of the denominator are a pair of complex conjugate numbers. That already means that. Which is exactly what we have. So this term has a pair of complex conjugate roots. So the highlighted term here corresponds to the, or should correspond to the highlighted term in the tables. Yes? I can't hear you, sorry. Complete the square. Okay, that's a, so you are talking about this one. You can. So the way the question is asked, you can use case 20 to complete the square, or can use case 22, as I am going to. Now, why I don't, so in the exam, if this is the question, use 20 if you find it easier. No problem, full mark. Why I want to do this case, because at least for this course, these terms, psi, and this term, omega n, are very important, especially psi. They are very important parameters of a system. So Later on, from lecture 7 onwards, you will really need to learn how to use these terms, these parameters. That's why this expression is more important, more useful than this one. So it's not wrong, just not as useful. So this term, I won't highlight. This term is fine, maybe for some other courses, maybe for vibrations or engineering mechanics, wherever you do vibration. This may be more useful. For this course, this term is more useful. After all, there must be a reason why both are given in the tables. So I'm going to solve it. Sorry, the break will come a little bit later, but let me just solve this one. So I want this term to be the same as this term. But there is already there is one difference, okay? It is normalized. The coefficient with the highest order term is 1, that's fine. But the numerator here is not 1. It is the same as this term here. So these two are the same. Over here, they are not. Here I have 2, here I have 1. So I'm going to artificially create 2 over here. So I'm going to write 1/2 times 2. Okay. So 1/2 times 2 is 1, so I haven't changed anything. Now, I'm also going to condition this denominator so it looks like the denominator in the tables. So I'm going to start with this coefficient. So I'm comparing 2 with omega n squared. So omega n must be equal to square root of 2, if those two are equal. So I have square root 2 squared. Again, I haven't changed anything compared with this. But I also want this 2 to be equal to equal to 2 psi omega n. Okay. So 2, this is omega n. Okay? So for the whole term to be the same as 2, this must be equal to 1 over square root 2. So psi equals to 1 over square root 2. So I know omega n, I know psi, so now I can write this expression. So I substitute omega n, which is square root 2. I substitute psi down here, which is 1 over square root 2. I do it here as well. I do it here as well. So finally, I get something extremely simple. E to the minus t sine t. So check that when you substitute those values, you should get e to the minus t sine t. Now, I agree that your method would be quicker for this particular case. But having completed this, your method, you wouldn't know what psi is. Psi is called damping ratio. You wouldn't know what natural frequency of this system is, omega n. That's why I'm doing this way. Again, for the first quiz, you are free to do any way you want. But for the mid-semester test, you will have a question asking, different damping ratios of different systems. So that's why you should start practicing using this one, or using this one, or using this one, these expressions. OK, any questions? OK, I think we deserve a break now, and then we move to the remainder of the lecture. Oh, right.
I'm not sure how did you get that CS plus T for that?
No, that's a rule. It's not how you get it. You have to write it that way. Sorry, I just muted because.
What is the number here? Something now?
Sorry?
Like 3 or something?
No. Doesn't matter what if you have a second order polynomial, this one has to be a first order, n minus 1.
Oh, yeah, I remember.
You can get a fifth one, then this one has to be a fourth order.
Is there any way you'd be able to turn on the seat power?
What was that?
The PowerPoints under all the seats, none of them.
Oh, okay, possibly room control. No, I have lights, screens, and air conditioning. But they had, I remember these guys were struggling also. Some of the PowerPoints did work last time, some didn't. So sorry.
You know how we have UT for time limit, and in table it says UT transforms to 1 of S. Is the same U as?
Okay, this is shift theorem, so you don't have shift theorem in the tables. You will be given this expression, not this expression, but yeah, the shift theorem. You'll be given this expression in your exam sheet.
What about this one? Wow.
No, this is U of t, which is not shifted.
Oh,
But this U of t is shifted by A. Okay. So what you have in the tables is something that goes like this. It jumps at 0.
yeah.
When time equals to 0, jumps up to 1.
So
But when you have a shift, it actually delays the jump by A.
So when
by A.
it's not shifted, it's just 1 of
That's
S.
it, yeah, yeah.
Do you get U of t all the time with
If you do inverse Laplace. I said that on Friday. I get U of t every time, you don't have to. If you forget it, you're not going to be penalized. Yeah. Yeah. You know why? Because the tables don't have U of t. Okay. But the tables don't have U of t because they do Laplace from here to there. They don't go backwards. When you go backwards, you actually, as I said, you destroy the function for time less than 0.
So when I go reverse, I always get.
Strictly speaking, you should put U of t, but because in the exam you were just copying, you find your function, you copy over here, you forget U of t. I don't want to penalize that. Okay. Yes, I think he was first, sorry. Yeah.
Can I just clarify what you said? So the input function doesn't affect the transfer function, right?
Yeah, the form of the input function.
Right.
The form, yeah, okay.
So if the input function, like you said, was like an impulse or
Yeah,
something,
yeah.
you Laplace that, and you could like sub that into here, then count, like times that across, and that gives you output.
That's correct. But the transfer function does not change.
Yeah.
Yeah.
But like that only works if you assume the initial conditions are all 0, right?
Yes,
But then
yes.
if the initial conditions were 0, how do you like? make
Oh,
that
you
0?
go back to the differential equation, and then you Laplace the differential equation.
Or
And
if
then
you
the
want
second derivative will give you 3 terms. One is s times x of s squared times s of x, and then you have minus one term and one the other term corresponding to velocity at 0 and displacement at 0.
So then you can't use this.
So you can't use it. That's right. That's it. Okay. Yeah.
Yeah, this doesn't make sense. It's sort of, like to me, you'd be getting the 0 value with just these functions alone. Because they're the same function.
Oh, but this, okay. But we said this is more descriptive than mathematically rigorous expression. So we say this second one exists only between b and infinity.
Yeah, but at the value from B onwards, it'll be taking the same value as this. So
Sorry, I didn't bring my glasses. I look here. Sorry. Okay.
So now I see it's like this is growing.
Yeah. Okay. From 0 into infinity.
And so
This
that's-
one is a negative a over b, which exists only between b and infinity.
and they take on the same. So it exists from B, but from the point B onwards, it's going to be taking on the same value as this one, right? So it's,
Yeah, well, yes. But as I said, this is not a mathematically rigorous expression. This is a description that this new RAM function, is shifted by B effectively. It's shifted by B, and therefore this shift. What I did at the beginning of the class is mathematically rigorous. So this is descriptive. Just treat it as a description. Yeah.
Just one question. For these two, right, for this part, do we use radian or degree for the equation?
Radians.
Radian.
Radians.
Yeah, okay, thank
Yeah.
you.
Yeah. Okay. Now, before we continue, there was an interesting question during the break. Okay. Here, so the question was, in this expression, do we use radians or degrees? We use radians. So here again, you use radians. That's pretty much all. So in these two cases, use radians, not degrees. Okay. To finish lecture 2, we have two methods that can be simpler than using partial fractions. Okay. Okay, one is the, sorry, up here, residue, the method of residue, and the other one is called method, Heaviside expansion method. So if you have a function of s, which is, once again, usually is the ratio of the one polynomial in the numerator, one polynomial in the denominator, how can you find the inverse Laplace transform quicker than doing those partial fractions? Well, once again, you have to factorize the denominator, and unfortunately, this method works only if you have a real, if all roots are real. The roots of denominators have to be real and unrepeated. So you can't have s plus 3 squared. Then this method doesn't work. There is a way it works, but not the way explained here. So if all roots of the denominator are real and different, you can apply this. Now, those roots, we can call them AI. So A1, A2, A3, up to how many roots you have. So what you do, you multiply your original function with the term corresponding to the first root, and then make s equal to minus that particular, s equal to that root, in fact. S equals to minus AI. Okay? Where I is the ith root of the denominator. Let's do the example just to make it clear. So if this is f of s, and you want to find the inverse Laplace transform, well, first of all, there is a part which is not factorized here. When you do, you will get s plus 4 and s plus 8. So f of s equals residue 1 over s plus 1 plus residue 2 over s plus 4 plus residue 3 over s plus 8, which is similar to A, B, and C. However, the way you find R1 is to take the original function, which is s, where is it? Okay, sorry, it is up here. 3s squared plus 2s plus 1 over this denominator, and multiply this original function with the term corresponding to the first root, which would be s plus 1. Okay, multiply that by s plus 1. Now, this s plus 1 will cancel s plus 1 in the denominator. And now multiply, substitute s with minus 1. So you have minus 1 here, minus 1, and plus 1. So minus 1 squared is 1 times 3 is 3. 2 times minus 1 is minus 2, plus 1, that will give you 2. Down here, s is minus 1, so you have 3. S is minus 1 plus 8, it's 7. 3 times 7 is 21. Repeat the same for s equal to minus 4. So first we will use s minus 4. So you have s. You will lose s plus 4. So you get s plus 1, s plus 8. Everywhere you have s, you should put minus 4, and you will get minus 41 over 2. Residue 3, now you're losing s plus 8. Okay, so you have these two roots left. Make s equal to minus 8, and you will have 177 over 28. So f of s now equals 2 over 21 s plus 1, minus 41 over 12 s plus 4, and plus 177 over 28 s plus 8. Finding inverse Laplace transform should be easy. Just use tables. You have 3 exponential terms here. Now, Heaviside expansion, again, is about finding an inverse Laplace transform of a function given as a ratio of two polynomials, P of S and Q of S. And here, well, first of all, the same limitation applies. So the roots of Q of S have to be real and unrepeated. And if that's the case, what you do is differentiate Q of S with respect to S. Keep P as it is. Keep the numerator as it is. So numerator divided by the differential Q prime of S. And substitute S with the first root and multiply by e to the minus first root times t. Okay, so you go straight into time domain. You don't even use the tables. A simple example, S plus 2 over S plus 3 times S plus 1, that's P of S over Q of S. First thing you need is Q dash. Differentiate Q with respect to S. D by ds of, you expand this, S squared plus 4S plus 3. S squared gives you 2S. 4S gives you 4. 3 gives you 0. So now you have S plus 2 over 2S plus 4. Make S equal to minus 3. And multiply by e to the minus 3t. Why minus 3? Because that is the first root. Repeat the same, but this time s equals to minus 1. That is the value of the second root. And you multiply by e to the minus t. E to the minus 1t, because minus 1 is the root. So the inverse Laplace transform will be this. 1/2 e to the minus 3t plus 1/2 e to the minus t. If you use the tables, I'll leave that to you, you should get the same expression. Okay. That's lecture 2. Any questions? Okay. Now lecture 3. I was hoping to start this a bit earlier. Lecture 3, I have to warn you, is probably the most dangerous lecture in this course. The most slippery one. Why? Why is it so dangerous? Because it looks so simple. Everything I'm going to tell you today, you will say, well, but we know that. And that's where the trick is, because I'm telling you things you know in a slightly different way. Every component here that you have seen so far in other engineering courses will be approached from the point of view of creating transfer function of that particular component, that particular device. In previous courses, you didn't have to do it. So we are addressing well-known things, but from a slightly different aspect. So don't fall asleep, although it's not difficult. When you see a spring, for example, so when I say the differential equation describing this spring is F equal x, k times x, you will say, of course. What's new here? Why are you lecturing this? But you will see later. This is actually the differential equation describing this particular device called spring. Differential equation. The order of the differential equation is 0. There are no differentials, but it is still a differential equation. So, as you are going to see later, when we apply the Laplace transform to this differential equation, we'll get the transfer function. Okay. In this case, very simple, but we'll see as we go. Okay, so the first device here is a standard spring, a linear spring. So you apply a force, as we had before, you apply a force, the spring, in this case, probably compresses by x. So the relationship between the force and the displacement of the spring, F equals kx. Very simple. The second spring here is torsional spring. So you apply a torque, and there will be angular displacement. Okay? And the relationship between the torque and angular displacement is now gamma equals k theta. Okay? Where k is also stiffness, but the unit of torsional stiffness is different. It's Newton meter per radian, whereas here stiffness is Newton per meter. So it's a different kind of stiffness, but the relationship looks extremely similar, these two relationships. Now dampers. or viscous dampers, as we often call them. Now, this theater doesn't have the dashpot on the doors. Well, actually, it has, but it's probably on the outside. You've all seen, why, our friend just moved in and the door didn't slam. So thanks for that. But it's not what you did. It's actually whoever designed the door. They put those dashpots, or how you want to call them, cylinders filled with oil with a piston moving inside. And there is a spring as well. So when you go through the door automatically closes behind you, thanks to the spring. But if you only have a spring, the door will slam. Okay? This viscous damper reduces the velocity of the spring, or actually generates resistance, which is proportional to the velocity, relative velocity between the piston and the cylinder. Here. So actually you have, this device is sometimes also called leaky piston. So you have a piston with a hole in it, so it can move through the cylinder. And the oil actually flows either through that little hole, or the gaps around the cylinder, around the piston are big enough. Okay, maybe I should draw this to explain a bit better, but just at this stage, accept this, that the force in the viscous damper is proportional to the velocity. With the spring, the force is proportional to the displacement. Force proportional to the velocity. And if you have a case that both the cylinder and the piston inside the cylinder, they move, one displacement is x1, the other one is x2, that the force will be equal to the relative velocity. So the difference between the velocity of the piston and the velocity of the cylinder. Okay. And you may also have a rotational viscous damper. So you have a disk moving through oil instead of a cylinder moving in a linear fashion. Then the relationship is, again, very similar. Torque gamma equals to C, which is a coefficient of viscous resistance times the difference in angular velocities between two ends of this shaft or whatever it is. Finally, inertia terms. So if your mechanism you're trying to model, you're trying to write differential equation describing your particular machinery. So if it has a mass, if you have a part whose mass you can't neglect, then that mass as it moves will experience inertia. So inertia, mx double dot, will be equal to force acting on this mass. Very simple, something we already know. Same for rotational motion. So a torque will be equal to moment of inertia times theta double dot, angular acceleration. Okay, we'll get back to these three a bit later. Now, if your machinery has a lever, it is usually good news because you can write two equations instead of one. So lever with 3 points, all three moving, okay? But the lever is rigid, so the lever is, remains in a straight line. Then you can write an equation that links the three displacements, so geometry equation, or you can write an equation that links the three forces, so force equation. For both cases, we use the superposition rule. How do we write a geometry equation that links x1, y, and x2 into a single expression? Well, let's say we want to express y as a function of x1 and x2. First, we assume that x2 is 0, so you have a fulcrum here. So in that case, you express y in terms of x1. Then you move your fulcrum over here, and then you express y in terms of x2. And add those two components of y to get real y. Okay, if x2 is 0, if the fulcrum is here, then you use the rule of similar triangles. Of course, the assumption here is that those displacements x1, y, and x2 are small displacements, so you can assume they are linear. So those points are moving along straight lines. If those displacements are not small, then you have circular, or should I say angular motion, or even circular, if they're really big. So assume small displacements. Okay. So if they are linear displacements, then you can use similar triangles here. So you can say that y in the first case, when x2 is 0, equals to b over a plus b times x1. Second case, if the fulcrum is here, so y in terms of x2, you have a different pair of similar triangles. So in that case, y will be equal to a over a plus b times x2. And y will be equal to the sum of the two. So this is y. And this is really the equation that links three displacements. Geometry equation of the lever. The force equation, again, you can do the same thing. Fy, which is this force, will be equal to, first assume the fulcrum is here, but this time you write a moment equation about this point. So Fy times b will be equal to F1 times a plus b. Okay? So Fy only equals a plus b over b times F1. Here, Fy only equals to a plus b over a times f plus b, times F2. So you have now Fy expressed in terms of F1 and F2. Gears, or not necessarily gears, you can have drums that use friction, but anyway, so two rotational objects that are meshed together. So the tangential displacements are the same of each of the gears, each of the drums. Gearing ratio is defined in the ratio of the two diameters, which is the same as we know as the ratio of two radii. Remember, angular velocity, or theta dot, it would be equal to x dot times r, or divided by r, pardon me. Okay, and x dot, that's the tangential velocity here, which is the same for both gears. So you can write that n, gearing ratio, equals d1 over d2, or it is equal to, it will be reversely proportional to angular velocity. So omega 2 over omega 1, or theta 2 over theta 1, theta 2 dot over theta 1 dot, theta 2 double dot over theta 1 double dot. So the ratio of accelerations as well. Or now back to, if you want the ratio of the torques, it's gamma 1 over gamma 2. Okay. Nothing you haven't seen so far. Electrical components. We are going to deal with three electrical components in this course. One is resistance. The equation describing this particular component is here. So the current through the resistor R will be proportional to the voltage difference and divided by R, which is resistance. Capacitance, current through the capacitor, if you have voltage before and voltage after the capacitor, will be proportional, current will be proportional to the derivative of the voltage difference with respect to time, times C, which is electrical capacitance. Or you can rewrite the voltage difference equals 1 over C integral of I dt. Because what the capacitor does, it integrates the current coming into the capacitor. And inductance, so if you have a coil, there will be inductance taking place inside this coil. So once again, you have voltage difference. As a result of the voltage difference, you have a current flowing through the inductive coil L, inductance L. I will be equal to 1 over L integral of voltage difference, or the opposite, voltage difference equals to L di by dt. These three equations, again, are going to be given in your exams if you have an electrical system in the question paper. Or they may be given even if you don't have an electrical system, just to see if you know how to differentiate equations that you need and equations you don't need. Okay, now we can talk about impedance. Well, we already probably know what impedance in the electrical engineering, in electrical systems, electrical circuits is, but we can expand that idea of impedance to other mechanical systems as well. And we'll do it by all these equations that not all. Some of the equations we had so far will convert into Laplace domain, into S domain. So once again, if this is the equation describing the spring, in the S domain, it becomes a very simple expression again. F of S equals K times X of S. Damper, because you have first derivative here and first derivative here, you will get S times x1 minus x2, assuming no initial conditions or zero initial conditions, because this is leading us to the transfer function, to the creation of the transfer function. With inertia, you're going to have the s squared term because you have second derivative of x in the time domain. Okay. Now, this means that you can think of stiffness of the spring as impedance. Cs, impedance of a viscous damper. Ms squared as impedance of a mass, or inertia. Okay? Let's do the same with the resistor. In the S domain, you have I of S equals to voltage difference over R. Very simple. Capacitor, because of the derivatives, you will have S here. And finally, because of the integral, you will have 1 over S, but this should be lowercase s. Try to correct this if I don't forget. So this is lowercase s to avoid confusion. Okay. So what we are saying here, if you think of a force in a mechanical system, if the force drives a process in your system, okay, so F is the driver, F is the input, then X becomes the output, or the consequence of that process. In the electrical system, it is the voltage difference that drives the process, and you have a current as a result of that input. Okay, now let's see when you have an electrical circuit like this. First of all, in series, these three components connected in series, then those three components connected in parallel. So you have voltage here, V. Here voltage is 0, so the difference between input and output voltage is V. V will be equal to voltage across R plus voltage drop across R plus voltage drop across C, then voltage drop across L. Voltage across the resistor is Ri. Voltage across the capacitor is 1 over C integral I dt. Voltage across the coil, across the inductor, is L times di by dt. Laplace transform will give us now V of S equals to R times Is plus 1 over Cs, where S comes from the integral, and plus Ls, where S comes from the differential. Okay, so in case of a connection series, you have a sum of voltages equal to the total voltage. In case of a parallel circuit, you have a sum of currents. So the current through each of these components, the sum of these currents will be equal to I, the current here. So now I becomes equal to I1, and I1 is the voltage over the resistor, across the resistor divided by R, so V over R. Current I2 will be equal to C times dV by dt, and current I3 will be equal to 1 over L integral of V dt. In the S domain, I of S equals to Vs over R plus CSV. Cs comes from the differential. And here, 1 over Ls, where this S comes from the integral. Okay. We actually applied what is known as Kirchhoff's law. Or actually two of them, one in each for each case. Okay, so much about electrical problems, electrical systems. Thermal. When you have a thermal process, Okay, you can have a number of different types of thermal processes. Think about a wall. And this wall has two temperatures on two different sides of the wall, just like any room that has a different temperature than the ambient. As a result of the temperature difference, there will be a heat flow through the wall. So the heat will flow, obviously, from the medium, from the side of the wall that has higher temperature towards the side of the wall that has lower temperature. The heat flow will be proportional to that temperature difference, will be inversely proportional to the thickness of the wall, the thickness of the wall, will also depend on the area of the wall and some coefficient, K, coefficient of heat conduction, obviously. Okay, so now if the temperature difference is the drive, is the input, then the output will be heat flow, the rate of heat flow, okay, times some constants here. Heat convection, slightly different, but again, it boils down to the same thing. You have a surface with temperature T1 and the surrounding medium temperature T2. So the convection, the rate of heat will be equal to Hc, which is the convection coefficient, times area, the surface area of the solid object, times temperature difference once again, because it is the temperature difference that drives this particular process. Thermal capacitance, or should we call it the rate of change of internal heat. Now, you take any object you want. Someone forgot this, so I will use this for this example. If you are bringing heat into this object and also taking out heat from this object, those two rates of heat are not necessarily the same. If they are not the same, this object will either heat or cool. If the rate of heat in is exactly the same as the rate of heat out, it will stay at the same temperature. Okay. So the rate of change of internal heat is rho CV d temperature by d time, where rho is the density. Let's assume homogeneous material here. Volume, V is volume, so rho C is also equal to mass, so we can say MC. Okay, C is specific heat. Q is the rate of change of internal heat, but it is also equal to, as we call it here, net heat flow. So all heats in minus all heats out, that's the net heat. Okay. So again, we can relate the input and the output through these constants. We can call them impedance, or later on we'll call that transfer function, exactly. Thermal radiation is a very nonlinear process, so what we are going to do is linearize it, but this linearization will be accurate only over a very short, very small range of temperatures. Okay, why? Because, because the rate of heat due to the radiation is a function of temperature, absolute temperature to the power of 4, which is very nonlinear. A is area, sigma is Stefan's constant. Stefan's constant, in fact. Okay, so how do we linearize this? Remember the linearization expression. So Q will be equal to the value of the function at the operating point. That means T naught to the power of 4, plus T minus T naught times the value of the derivative at the operating point. So we need to find the derivative of this, which will be 3A sigma T cubed at the operating point, so therefore the subscript here. Okay, so here is the linear expression for the rate of heat due to radiation. A little bit about fluids. So if you have a pipe and our fluid is flowing through the pipe. At one end of the pipe, there will be pressure 1. At the other end of the pipe, there will be pressure 2. The pressure difference is proportional to flow Q, but times this, let's call it resistance. Usually comes from the friction between the fluid and the walls of the pipe. Now, in this case, the fluid can be either liquid or a gas. Doesn't change very much. Capacitance. Now, if you're bringing a mass flow m dot into a rigid vessel, into a volume, or into a vessel of constant volume, then m dot will be equal rho v is mass, differential of rho v by dt. If you agree that this is absolutely rigid, then volume becomes constant, so you have d rho by dt. Now, if this fluid is a liquid, then what you can write is that the pressure difference, so P minus P naught, whatever the initial pressure was, will be equal to beta times rho minus rho naught over rho naught, so relative change of density. This is a discrete form, or in the differential form, P dot will be equal to rho over rho naught times rho dot. Remember that rho dot equals m dot over v. So now we can relate m dot as our input, and P dot, rate of change in pressure. So mass flow m dot is the input, rate of pressure would be, rate of change of pressure would be the output. If our fluid is a gas, use the gas equation. M equals PV over RT. M dot, again assuming constant volume, divided by R and T, assuming constant temperature as well, to keep it as simple as possible. And then you have the rate of change of pressure. So again, you have a similar expression, V over RT times P dot. Fluidic inertia, if you're ever going to need it. So when you have a mass of fluid moving through the pipe, it will have its own inertia. Mass of fluid M equals rho V, and V equals AL. Area A, area of the pipe, times the length of the mass of fluid we are considering. Okay. What is the force acting on this fluid? Well, it is equal to A times pressure difference, P1 minus P2. F equals MA. F equals P1 minus P2A. MA, we said that M was rho AL times acceleration A. A equals, in fact, L double dot. If L, we assume to be the axis that describes the length of the pipe. L double dot equals V dot. Okay, V dot is acceleration as well. But V equals Q over A. So the flow, volume flow, is Q divided by A. That will give us velocity. Because it's velocity dot, we have Q dot here. So finally, the pressure difference will be proportional to Q dot. So in case you can't ignore the inertia of the fluid moving, this would be the equation. And finally, if all this scares you, these are two very simple rules for thermal and fluid systems. So for thermal systems, you have your control volume that you choose. And you observe where are the heats coming in, where are the heats leaving that control volume. The difference between the two, or the net heat flow, will be equal to d mct by dt. And now, depending what is constant in your case, what is not, maybe you can, instead of m, write rho v ct by dt. Okay. So if this theater is our control volume, So think about the heat coming in. So it is being cooled, so the heat is coming in through the walls. Unfortunately, heat is coming through the open door, but the heat is taken out because we are getting cold air coming, or cooled air coming in here. Or if you want to be really, very accurate, then all of us generate heat as well. So multiply what is the usual thermal power of a human. It's about 120 watts rather, times how many people. So that is also heat in. So sum of all rates of heat in minus sum of all rates of heat out, and we'll see whether this room is cooling or heating, whether the rate of change of heat is positive or negative, or possibly zero. Similar with the fluids, so you take mass flow in, mass flow out. So identify your control volume, see where the fluid is leaving, that volume, where the fluid is getting into that volume, and the difference will be equal to rate of change of mass, which is the same as rate of change of rho v with respect to T. Okay, transducers are devices that convert one type of variable into another. So with mechanical systems, you have a spring converting force into displacement. So that's kind of obvious. Electrical circuits, they convert voltage into current. Input voltage is the input, current is the output. So that is fine as well. But these devices, we have only 4 examples. So in this case, pressure is converted into displacement. So displacement is a function of pressure. So here, again, you have a pressure cylinder, but here you have a diaphragm that is not rigid. So as the pressure is changing, so does the displacement of this point here in the middle of the diaphragm, this displacement x. So the question for you, we are not answering today, the question for you to think about is which of the 3 lines here, these dashed lines, are the correct description of this system. So you have pressure, and you have x-axis here. So which line correctly represents what is happening in this system here? Second example converts angular displacement into voltage. So this is a mechanism. Some windscreen wipers in some cars, they work like this. Some others have a crankshaft. So if this is how they work, let's see. So if you have this lever, this bar, moving along the theta coordinate, so making angular displacement, what happens? The slide contact will change voltage. So how does voltage change with theta? So you have 4 given possible answers. This straight line, this straight line, this looks like an inverse sine, and this looks like another inverse sine or inverse cosine or whatever it is. So think about that, and I'll ask you later on. Here you have a dish with a mass flow of some sort of liquid. So as the liquid flows in, the weight changes, so this piston will move down. As it moves down, the pressure, here you have a gas. The gas gets compressed, so the pressure changes. But at the same time, you have a flow of the same fluid out through this valve, and the valve has resistance R. So the question is, how does this pressure P rather change? How does it change with m dot, with an increase or decrease in mass flow? So you have 2 possible answers, this curve or this curve. And finally, you have a displacement x. As this piston moves left or right, this pressurized fluid, escapes through this orifice. So as x increases, the opening of that orifice changes. So you have more of that orifice open, so therefore you will have more flow, m dot. Now you have 3 possible answers, this one, or this one. Okay, I'll leave that to you. That's your homework. Okay, any questions? No, we are not finished. Still have 7 minutes. Once again, if you don't have questions, I really want to ask you, don't ignore lecture 3 as simple as it sounds. Because once you start analyzing more complex systems, you will get back to the viscous damper. You have to get back to inertia, get back to those electrical components. Okay, here, this one. I'm not really starting lecture 4, but here you already have a spring and mass. So those two together. The good news is I have done this example earlier today. So it will be easy for you. Okay, any questions? Okay, that's it for today. Oh, why not? Yeah. I'll give you. Yeah, I'll give you one for each of the tests, and for the final exam. Yeah.
Would that get put up this week?
Yeah, why not? Yeah, but next week you have. You actually have. Yeah, in 9 days you will have a quiz, the first quiz. Yeah.
For laboratory, what week does that start?
Sorry.
Laboratory, what weeks?
I still don't know. I mean, I said definitely not until 6, more likely 8. Yeah.
Do we need to remember all of these equations?
No, absolutely not. No. Your problem will be, when I give you a list of equations, the only problem is to decide which equation applies to your system, to your problem. Not to memorize equations. Absolutely not. That's not the idea.
For the exam, can you maybe upload formula sheet or something?
No, what your friend asked me, if I upload one of the past quiz papers, you will see the list of equations I provided. So that will also give you the idea how difficult it is going to be. Yeah. So I'll do that.
Question.
Sure.
You have time for a
Yeah.
question? I didn't really understand the part about the levers and how you came to the...
Sorry. Just what's happening here? Oh, okay. Okay, thank you, thanks. Yeah, lever, sorry. Yeah, what about it?
I didn't really understand how you got to the displacement equation and the force equation.
Oh, excuse me, should I close this window now?
Yeah, it's fine.
Just close it.
Yeah, just close it, fine.
Okay.
Yeah. Thanks.
Oh, I closed. Do you have the lecture notes? How I got those equations? Yeah, I can show it quickly. Yeah, I can show you. Where are my pens? I can't believe it. Sorry, are they underneath? Oh no, they're here, already packed. Look. I thought someone stole my pens. Okay, so when you have a lever, A, B, C, and how did we call it? X1, X2, and Y. Okay? Now, Y equals to Y, let's call it Y of X1 plus Y of X2. Y of X1 means this point is fixed. Okay? So now you have A and B. Now we have similar triangles, so Y of X1, no, yeah, Y of X1, Y of X1 over A plus B equals to X1 over, no, sorry, Y over X1 over B, my fault, X1 over A plus B, okay? Why? Because this triangle is similar with this triangle, with this big one, okay? Now, Y of X2, now you have these two triangles, Y of X2 over A equals to x2 over a plus b. So now y equals this, okay, which is b over a plus b x1 plus this, which is a over a plus b x2.
Oh, okay. So yx2 and yx1 refer to the line.
Yeah. Yeah. So first we assume this point is one point is fixed, then we assume the other point is fixed.
Okay.
But because they are both moving, we use what we call superposition rule. We add them together.
Thank you.